Okay, well, last time we talked about filtering and introduced a couple websites, falstead.com. Hopefully, you had a chance to take a look at the digital filters in the Fourier series apps. They're intriguing, and you can spend a lot of time playing around with the different filter options, the inputs. You can even input your own MP3 file, and then there are different kinds of filters, and you can adjust the cutoff frequency and the order, and so it can lead to endless entertainment, almost, and of course aggravation for those who happen to be sitting around you, listening to those weird sounds. Um, So now we're going to continue on. We're going to present some examples. We're going to talk about some time series. And one of the time series that we're going to talk about, we're actually going to synthesize a climate forcing, the astronomical forcing associated with the Milankovitch cycles. And this is another good site to visit because these images are actually animated, and there are a sequence of them that explain and go into more detail on the Milankovitch cycles. So this is a good site to visit, but there are basically three cycles. There's eccentricity, which is roughly 100,000 year cycle from almost circular to highly eccentric and back again. There's obliquity, which is the tilt of the Earth's axis, and that's a 41,000 year cycle. And then there's precession, kind of the wobbling top. And that's on the order of about 21,000 years period. So here again, just taking a look at axial tilt, also referred to as obliquity, and 41,000 years or so. The precession is a more rapid, more rapid variation, and it occurs over about a 23,000 year period. So, in this particular slide, although you run into variable periods depending on where you look. And so, when we actually look at data, we'll get slightly different answers. So, but at any rate, then we have eccentricity, which is about has a period of about 100,000 years. So, at different times of the year, for example, in January, we're actually a little bit closer to the sun than we are in summer. In winter, we're closer than we are in summer. But if you're in the northern hemisphere, your axis is tilted away from the sun, so you're receiving less radiation, but you're closer to the sun, so you're receiving more radiation than you normally would. And then, of course, as this angle changes back and forth, then the northern hemisphere doesn't affect the equator so much, but the northern and southern hemispheres get more light during the course of the year when the inclination is greater than when it's less. So these have rather obvious impacts on climate. And if you look, here are a couple sites that if you want to find out more about Milankovitch forcing. These are cycles which have been extracted over a million-year period of time. And for precession, this is the shorter cycle, 19, 22, and 24. You'll see that there are different peaks that come out: obliquity 41, eccentricity 95, 125, 400,000. And I've seen these kinds of variations in oxygen isotope data from various parts of the world as well. So there's not really a single answer, which, there are other things that are usually going on. And solar forcing, the variations in solar output, and then we see the periods of glaciation are noted here down at the bottom. So quite a lot going on associated with these Milankovitch cycles. So if you recall, if you had a chance to visit, see the previous video, the time series that were being used there were fairly complex. The piano, somebody speaking. Now the Milankovitch time series, we can simulate one. We can make it fairly simple. We can put cycles in with 100,000 year period. So this is in millions of years. So 100,000 years would be 0.1 million years. The tilt, varying around 40,000 years. And the precession, somewhere around 20, a little less than 25 here. So we just simulate it. We just generate a sine wave and generate these three sine waves with these three different periods, and then sum them all together so that we get this composite response, and that has all three components embedded in it. So you can see the longer period one. You can see a little bit of the tilt in there. It seems to be kind of obscured, and then the precession is. And another thing that we haven't talked about is how do you scale these? And we put the eccentricity and the precession in at 1, at an amplitude of 1, with the tilt at an amplitude of 0.5. So it does come in at a little bit lower amplitude. So that in this time series here, we've, on top of these three components, we've added noise. So there's some random noise that's been added in here, which we'd expect noise to be present for other things that are going on, both astronomically and on the Earth, other factors which influence this time series. So if we take the Fourier transform of this noisy Milankovitch time series, well, the noise falls into the background, and then we can see three peaks. We can see that they're scaled. We've got two large peaks here. We've got one small peak. We can figure that this is probably obliquity. It's happening at that 40,000 year period. So we're just expanding this area here. We're looking at these peaks, and now we're looking in frequency. So this would be 10 cycles per million years, 20 cycles per million years, about 24 cycles per million years, and corresponding to these periods. So if you take the reciprocal of the period, which as we were expressing it in terms of millions of years, so 100,000 years would be 0.1. 1 over 0.1 would give you 10, and so on for the other components. So we have eccentricity, obliquity or tilt, and then precession. And so the next thing that we're going to talk about is filtering, and we've got this 10,000 year or 100,000 year component, 10 cycles per million year component that we want to filter out. We want to get rid of everything else. We want to get rid of the noise. We want to get rid of the obliquity and the precession, and we just want to look at this. So that's one of the neat things about Fourier series, is this aspect of filtering, and we haven't really talked about it, but convolution in time, and this is something that you can check into on your own. Convolution in the time domain corresponds to multiplication in the frequency domain. So we're just multiplying this low-pass filter, so you can just see we have a function in here which is high over here and then drops off to 0 over here. We're multiplying it times the amplitude spectrum, the Fourier transform of this time series here, just to extract this component. The only thing that's going to come through, the only thing that's left after we go through the multiplication, is going to be this peak. And then we take the inverse Fourier transform, and that gives us the basically the eccentricity. You can see that it's a distorted version of the eccentricity because the eccentricity that we used to simulate the signal had constant amplitude of 1 all the way across. So noise has had an influence, the background noise has an influence in producing variable peaks in the spectrum, or in the inverse Fourier transform. So, and then we can also go after, let's say, the higher frequency peak. And again, in our input, we had constant amplitude of about 1/2. And you can see probably on average we have about an amplitude of about 0.5 or 0.6. I forget what it was. But another thing that kind of goes beyond what we're going to get into here is that if we did go through the filtering process in the time domain, it would be a convolutional process. And the filter operator, which is a nice and simple looking feature in the frequency domain, turns out to be a complicated impulse response function or wavelet in the time domain, which we would convolve with the time series in order to get the filtered output. So if we go through a convolution process with this wavelet, we actually can also get this filtered data. Just another way to do it. So another example of filtering, we're going to take a look at a sonic log. This is just kind of the interval transit time between a transmitter and a receiver on a sonde or a vertical cylindrically shaped tool, which one lowers down the borehole and measures the travel time between the transmitter and the receiver, kind of a bit oversimplified. This is a log from the Central Appalachian Mountains, and we aren't concerned too much about the geology right here, but these are microseconds per foot, so these are delta t. If it takes a longer time to get from the transmitter to the receiver, then we have a lower velocity. So higher delta t's, microseconds per foot, correspond to lower velocities. Lower delta t per foot corresponds to higher velocity. This would be the highest velocity feature. This is a limestone, in fact, so it's fairly hard and fast rock. So if we take the Fourier transform of this, in this case, this is not a time series. It's sampled at constant intervals of depth. We get wave number. So this is just cycles per foot. So we still refer to it as an amplitude spectrum. We've got a really larger peaks over here at the longer wavelengths, and fairly low amplitude peaks at the higher wavelengths. And so coming down here and looking at the filtering process, we'll just take that same type of filter. I kind of cut off the peak here. So we just want to pass the lower wavelengths, which, think about what that's going to do. There's a lot of high frequency back and forth in here. High wave number, low frequency features in the spectrum. We're going to remove all of this over here. So these we're only going to pass the longer wavelengths, and we're going to get rid of all the shorter wavelengths. And when we do that, apply that filter, then we get, you can see where we've gotten rid of a lot of the background chatter, a lot of the what you might consider noise, which are, is probably small details in the geology, the stratigraphic section as you go down through the wellbore. But if we filter that out, we see some of and a geologist might be interested in this, or a geophysicist in particular. What are the things that we might see in a seismic data set? Some of the thicker intervals. So this limestone here is on the order of a couple hundred feet thick. It doesn't have a constant velocity throughout. It has a very high velocity at the top, and then it kind of drops. So we can look at individual features this way, and it might make a little bit more sense to us to clean out some of the noise. So this is just another example of what filtering can do for you. and we've just been presenting a couple examples here, and we'll have more on the site. You can visit the Geomath site or Tom's Geophysics YouTube channels, and we should have more videos on spectral analysis and filtering, Fourier series, Fourier transforms, and so on. So I hope for now, I hope you found this interesting, and that you'll keep an eye out for future postings, and we'll talk to you later.